In genetics, we talk about people who share a common haplotype, for example. If we're discussing mitochondrial DNA, which is passed on by a mother to all of her children, male and female, this is passed on in the form that she had it.
The mitochondrial DNA and DNA in general is very good at identifying individuals, and in things like paternity cases, at matching DNA, especially from a random background. You can be close to 100% accurate. You're never going to be 100% accurate, but you can be darn close to 100% accurate. So if you send your DNA to National Geographic and they say your ancestry is European, then I guess my question would be, well, with what accuracy level are you sure that it's European versus something else?
The fundamental question is, what is being sampled? It's been estimated that the population of the Western Hemisphere during pre-Columbian times had reached levels of 80 million inhabitants of North and South America. But then it has also been suggested that by the late 16th century, between 1500 and 1600, that population had plummeted to less than 10 million, from 80 million to 10 million, due to the exploitation of the native population by colonizing influences. And clearly that number continued to decline in the wake of Western expansion in North America and throughout the Western Hemisphere.
When Columbus in 1492 came to the Americas and made his first stops in basically the Caribbean islands and in Haiti and some of the islands around there, they estimated, or perhaps scholars since then have estimated, there was maybe in the neighborhood of 250,000 to 1 million people in those island areas. 50 years later, they figured there was about 500 people in those island areas, and 100 years after that, by about 1650, they believe they're basically extinct.
So the point being that the population that is being sampled today is a mere fraction of the genetic diversity that existed just a few centuries ago. So whether it's random or not begs the question of what is being sampled, and does that take into account the genetic diversity that existed at one time.
Some scholars believe that up to 80% of natives were killed off by either wars or diseases brought by the Europeans. There was a lot of people wiped out, a lot of history that went along with it, and a lot of DNA that would have disappeared as well. And so you reach these bottlenecks and lucky genes that can move forward, and other strands of DNA would have died out.
There have been some studies done by University of Utah geneticists, some of them LDS, some of them not. They have tested ancient DNA from all the Great Basin area, for example, mostly the Fremont culture, and they have found that the balance of mitochondrial DNA haplogroups was not the same among those people as it is among the Native Americans living in the same region today.
Individually, our genetic makeup reflects only a fraction of the potential genetic diversity represented in our genealogy, in our ancestry, because, for example, our mitochondrial DNA is passed down maternally. So I received my mitochondrial DNA from my mother, who received it from her mother, who received it from her mother. So if you think of that, that 4-generation chart, mitochondrial DNA only traces that bottom line on the chart. The mitochondrial complement of all the other lineages there, on that chart, what is it, 16 on the right-hand side, 16 individuals. 15 of the 16 have no representation in my genotype. Likewise, my Y chromosome, which is the other principal target or locus of interest because of its strict paternal inheritance, traces the upper line on that genealogical chart and only represents contributions from that paternal ancestor at the very upper right-hand corner of the chart. One again out of 16. So all the rest of that is not represented at least in my person. There may be other individuals, obviously, of my generation that have some representation, but they may not be sampled in the study, for example.
So if you come to a generation where there are no daughters, or, for example, if you have many lines of females that have this X haplotype, and as they go from generation to generation, if at any one point they do not have daughters, then that particular haplotype is lost. So if you're coming in with a very small group of people that may have a very small number of individuals that are having children and trying to contribute to this new population, that would be very, very difficult.
So I may have, say, back 5 generations, 4 generations, my great-great-great-great-grandfather was a fur trapper and married a Native American. Then my mitochondrial DNA would show me as a Native American, despite the fact that, say, all the rest, 90% of my cultural heritage, my genealogical heritage, came from, say, northern Scotland. So that's the potential bias and skew that can be introduced through admixture of populations.
When my wife and I have 5 kids, each one of those children has 50% of their DNA from me and 50% from my wife, right? So already we've reduced our DNA data set by half in these children, right? When they have children, their children, my grandchildren, will have a quarter of their DNA from me. So every time, in fact, every generation, you're diluting what was a single genome by half and half again.
Take-home point being that there is no population out there that is pure. All populations have experienced tremendous amounts of admixture.
So, and then you throw on top of that, in a population context, the concept of genetic drift and fixation of variants or loss of variants. What population genetics theory tells us is that eventually genetic variants will either go to fixation or loss. So either everybody will have the same variant or nobody will have that variant in a single contained population. Now that happens a whole lot faster when your population is small and a whole lot slower when your population is very large. So genetic drift, especially in a small population context, will erode variation rapidly.
We'd have to have him here, put a swab in his mouth or draw some blood, because the only way to find out what Lehi's DNA was like would be to have him give us a sample.
What is the effect of infusing a very small colonizing group, very small gene pool, a literal drop in the bucket of the gene pool of the existing indigenous population of the Western Hemisphere? And would we even expect to find a genetic trace of that inserted population?
There have been many individuals well versed in this area who says that we can only catch maybe a glimpse and perhaps now and again a shadow of what these populations looked at in the past. In fact, literature will quote that up to 64% of ancient haplotypes are now extinct.
It is not a scientifically testable hypothesis because, one, as we've already mentioned, you don't know what you're sampling today. It's a fraction of the genetic diversity that existed between 600 BC and 400 AD. And even if you could go back in time and sample and identify a Lehite marker, what would you compare it to? The gene pool of Jerusalem of 600 BC doesn't exist anymore. The Jews that occupy the Middle East today have virtually little to nothing to do with the Israelites of that time.
In Jerusalem at that time, there had already been major minglings between different groups, and so DNA was introduced from various parts of the world. So we don't have a standard to compare it by to say this is Lehite DNA.
The Middle Eastern area has historically been one of the most fought over areas of the world. There have been conquering armies that have come in and wiped out peoples, whole peoples, and flooded the area with DNA contributions from entirely different areas of the world. that has to have an effect upon the gene pool that's available.
Most of the Jews from Eastern Europe and Western Asia were converts, the Khazars and other ethnic groups that had nothing to do with the Israelitish bloodlines of that time. So you don't have A and you can't establish B, so how in the world can you possibly compare them to test your hypothesis?